Yeah, so I had one example here. Maybe I could just, where did it go? Just do it and then I'll be very happy. I lost it.
Oh no.
Here's somewhere. Oh, I forgot this whole page.
Oh.
Just kidding. Where is it? Sorry, I'm a little.
Are you sure you got a good night's sleep last night, Dr.
Did I get enough sleep last night? I don't know. I thought I did. Oh, yeah, here we go. This is what I was looking for. Find number 7, is it?
8.
8. Find all primitive roots of n equal to 18. And just so you know, I told you I was going to give you a table of the smallest primitive root. That's for every prime number. This is not a prime. Does this number have primitive roots?
Yes.
You can check. It has to be of the right form, and it is 2 times the power of prime. So this thing does have primitive roots. And how are you going to find any primitive roots of? How are you going to find all the primitive roots of 18? Find one. Find one. How are you going to find one? Brute force. Okay, so I agree. So they have to be relatively prime to 18, so I won't bother to test. So I don't need to test any numbers that have common factors with 18. So what would be the first reasonable candidate?
5.
5.
That's what I
I
meant.
know. So 5 would be the first candidate. And what does the order of a primitive root have to be? It has to be phi of the number, right? So phi of 18, which is what? Well, it's phi of 2 times phi of 3 squared. That's phi of 2 is 1, phi of 9 is 6, right? 9 minus 3 is 6. So we're looking for an element of order 6. And by the way, the order of every element has to divide 6. So if I take a number like 5, right, its order has to be either 1, 2, 3, or 6. And if you test 1, 2, and 3, and you don't get congruent to 1 yet, then it must be a primitive root, right? So that's pretty easy to do. So 5 to the first is not congruent to 1, mod 18. And 5 squared is not congruent to 1, mod 18. What about 5 cubed? 125? Mod 18, oh goodness, let's see. 18 times 6 is 108, isn't it? So 5 cubed is 17. 5 cubed is 17, which is negative 1 mod 18. So the answer is the order is not 1, 2, or 3. Okay, so it has to be 6. So it is a primitive root. Okay, so this implies that 5 has order 6. Right? So again, the order of any number has to divide the phi of n. So the order of 5 has to divide 6, so you can test the first 3 powers of 5. You don't get 1. You don't get 1, so therefore the order has to be 6. You don't actually have to do 5 to the 6th. Those of you who are looking for ways to save time on the test, you don't have to check 5 to the 6th because Euler's theorem tells you that every number raised to the phi of n power will be congruent to 1 mod n. So we have 5 as order 6. Okay, so that's one primitive root. How do we get the rest of the primitive roots once we have one of them? They're all powers of this one, aren't they? Right? Once you have one, you're looking for powers. And which powers are going to give you the rest of the primitive roots? The ones that are relatively prime to 18, and there's exactly 6 of those. Right? So the primitive roots would be, so we have 5 to the first, And then, so what other numbers are relatively prime to 18?
So,
So 1, obviously, 5, 7, 11, 13, and 17. So these powers of 5 would give them to me, right? Okay, so 5 to the first, 5 to the fifth, 5 to the seventh, right? I hope I find my notes here. Dot, dot, dot. Right, okay. No.
That's not right.
I'm not doing this right. Okay, hold on a second. So we found one primitive root. Hold on, I gotta back up a second. So we have 5 to the first, obviously. Remember that the order of, go back to this for a second. The order of any power of an element is equal to, this is by Theorem 8.3, I believe. The order of A divided by the GCD, do you remember this? The order of A with the power. Yeah, this is what I was supposed to be doing. Now, of course, the order of 5 is 6 already. So we're taking, in this case, 6, the GCD of 6 with H. I mean, the reason that I was pausing, because how many primitive roots should there be? The answer is phi of 18. So the number of primitive roots, there are phi of 18, which is phi of 18 we said was 6. What is phi of 6? How many numbers are relatively prime to 6? Just 2, right? Primitive roots of 18. There we go. So there's only supposed to be 2 of them. And so you just need to choose the H values that make the denominator equal to 1. And those are 1 and 5. So I should have stopped at 5 and the fifth. That's what I meant to do. Okay, good. So those are your primitive roots. There's only 2 of them. It says find all primitive roots of n. So figure out how many there are going to be. There's only going to be 2 of them. 5 to the fifth, of course, we could reduce that if we wanted to. 5 to the fifth is like 5 squared times 5. 5 squared is 25, but modulo 18, it would be 7. So 7 squared times 5. And 7 squared is 49, right? Which is, in the world of mod 18, 49 is the same as 15? 13? 36, yeah, 13. 13 times 5, so this is 65. Just trying to do it in my head, sorry. 65 in the world of mod 18.
11.
Thank you, 11. Yeah. So my 2 primitive roots are 5 and 11 in mod 18. But we could just, okay, so we found all the primitive roots, but then what I was trying to get to is, all right, then you can build this table. You can build this table right here. And I'm going to use the primitive root 5 to make my table. So what do? I write down all of the x's that are relatively prime to 18. So this table doesn't have 17 more columns. It only has 6 columns. The numbers that are relatively prime to 18. So it's going to have 1, we wrote them down over there. 1, 5, 7, 11, 13, and 17, right? Those are going to be the numbers that we're going to look at. And so we can start to fill out. So now we actually want to know what the powers of 5 are that we have here. So for example, the 1, the index of 1 is always equal to what? Like what power of 5 is going to give me 1? Easiest answer. 0, right? 0, yeah. I mean, 6 is fine, but 0 is easier, right? And then, so what's the index? Let's just make sure everybody understands that. What's the index of 1? You're just asking what power of 5 is congruent to 1. The answer is 0. And this is going to end up being mod 6. It's mod phi of n, which is mod 6 in this case. That make sense? Okay, what's the index of 5? Index of 5 is 1, right? The table always starts off this way. Underneath a 1, you're always going to have 0. Underneath your primitive root r, you're always going to have a 1. Now, probably the next number I would do wouldn't be 7 necessarily. Probably the next number that I would look at would be 5 squared. Well, 5 squared actually is 7, sorry. So 5 squared being 25 is 7, so therefore this is a 2, right? So the index of 7 is 2, because 5 squared is congruent to 7 in mod 18. Okay, so basically, so one way to think about it is, if you want to do the bottom row, let's suppose I ask you to make this table, right? You want to start with, obviously, 0 and then your primitive root are going to have this kind of a configuration. But what you did here is you multiplied by 5. And then to get from 5 to 7, you multiply by 5 again. And that's how you're building these powers up. 0th power, 1st power, 2nd power. Like 5 squared is 7. So what's 5 cubed? Well, 7 times 5, right? Which would be 35, which in mod 18 would be 17 or negative 1, right? So that's where the 3 goes. Right, so in other words, you've multiplied by 5 again to get there. Now you have 3, so 5 cubed comes out to 17. And actually, this is always going to be half of the phi of n. Yeah? We are. No, we're looking on the bottom row, we're looking in mod 6. But when I calculate powers of 5, I'm working mod 18. Yeah, there's always 2 different mods, right? There's the modulus of n itself when you're taking the powers of the primitive root, but then the index line, the bottom line, is being done mod phi of 18, which is 6. So the only numbers you're going to see me write on the bottom line are going to be the numbers from 0 to 5. So now I have to take 17. Now 17, I would rather think of that as negative 1. So on the top line, let me just be really certain everybody's with me on this. On the top line, I'm working mod 18. On the bottom line, I'm working mod phi of 18. This is always the way that you want to work with this table. So in mod 18, 17, I would rather think of it as negative 1. And when I multiply it by 5, I get what? Negative 5, right? But in the world of mod 18, negative 5 is the same as 13. So that means when I multiply by 5, I'm going to get this number. I mean, you could just take 5 to the 4th power, but it's a lot easier to take 5 cubed and just multiply by 5. Okay? And then obviously the last one has to be there. So, that's kind of how you come up with that. Yeah, right?
So always your powers are going to be 1, 2, 3, 4, 5 until you fill up the thing.
Mm-hmm.
Okay.
Yeah, I mean 5 has order 6, so by the time you get to 6, you're going to have the whole thing will have been finished. Okay? So guys, all of these numbers are powers of 5. That's one of the things about primitive roots. If you take all powers of the primitive root, you get all the numbers that are relatively prime to n. Well, there's 6 numbers that are relatively prime to n. So every single one of these numbers is some power of 5. And all we're trying to do on the bottom line of that table is say which power of 5 is each of these numbers. Okay, so this number is 5 to the 0. This number is 5 to the 1st. This number is 5 squared. This number is 5 cubed. This number is 5 to the 4th. And this number is 5 to the 5th. And you really, you aren't going to know that off the top of your head. You have to actually work it out. to like build this table from scratch unless it's given to you. So I had this exam, the last time I taught the class, I had this exam, and I asked the students to fill out one of these tables. But I gave them like 50 columns. And I said, oh, you don't need all of them. You only need some of them. So make sure, if I ask you that kind of question, see, in this case, you only need 6 columns. So you have to know what to fill out. On the top line, you're just putting the numbers that are relatively prime to n. And on the bottom line, you're just putting the powers that give you those numbers. Okay. Can everybody rewrite quadratic congruence, solve the quadratic congruences using the substitution, kind of the stuff you're doing for today's homework? That's pretty easy. I won't go over that. Oh, I think a really cool. Can I show you a really cool proof of something really fast?
Yes.
I'll make it fast. Wilson's theorem. Do you remember this? This is the last thing. I'm so sorry. I get excited. I got hung up on that one problem. That's the reason I'm running behind. But this is math, so it's fun. Okay, what does Wilson's theorem say again?
X squared equals 1.
No. Wilson's theorem. Yes. I would like to show you an amazing proof of this theorem. This is actually back from the stuff from the first test. But I want to give a new proof using primitive roots. Prove by using primitive roots. Okay. This is a very short proof, but it's absolutely lovely. So this will make us all smile when we head out. What modulus do you suppose I want to work with? Not everything is a trick question. What modulus do you think I want to work with here? P. Gee, I wonder why. Wait, if we're in mod P, do we know we have primitive roots? We do. Let's let R be a primitive root. Okay, now, we just said a couple minutes ago that if we start taking powers of that primitive root, what will we end up generating? All of the numbers that are relatively prime to P, which would be which numbers? 1, 2, 3, 4, 5, all the way up to P minus 1. Ooh, this is all of those numbers multiplied together. So would you agree that I could think of P minus 1 factorial as, this is all of the numbers, these are all of the numbers that are relatively prime to P, right? So would you agree that if I start taking all of my primitive roots, my primitive root R, and taking all of its powers, all the way up to the P minus 1 power, would you agree that I have to have all the same numbers there in some other order? If you don't believe me, go back to where we did the chart just like this for 17, and you'll see on the top line all the numbers from 1 to 17, and on the bottom line, all the numbers from 1 to 17 in some other order, right? Okay, so here we go. Now what do we have here? This is, can I simplify that? It's R to the what?
Squared.
I don't know, what do you do with exponents?
Add
Add them. So what's 1 plus 2 plus 3 plus 4 up to P minus 1?
n times
P.
I mean, P times P, right?
Hold on. Don't give me phi. How do we add up the first P minus 1? Don't use this class. Use something you learned before you. Thank you. It's P times P minus 1 all over 2. Love it. Okay. Exactly right. Okay, so that's my new exponent, right? Oh, but can I... How do you want me to do that, Anthony?
R to the P times R to the P minus 1 over 2.
Or
You mean like times that?
switch the
Let's try this again.
Oh, okay.
We have to get this right, but when we do, it's going to be amazing. R to the, okay, remember, we have a primitive root. It means the order is p minus 1. So the order is p minus 1. So do we know anything about any of the other powers of r? Go ahead. What is the, so I know what this is, right? And then there's a p here. What is r to half of its order if we started with a primitive root? -1, right? That was our homework problem 6a again. Raised to the pth power. Okay, if p is equal to 2, this theorem is true by looking at it. You can write that. So I'm going to assume p is an odd prime right now. And then this is -1. Okay, so this would be for every other, so this proof works for every prime except 2. Okay, isn't that nice? And what a neat thing, it reviews several things. It reviews the fact that the primitive root, powers of primitive roots generate all the numbers from 1 to p minus 1. It reviews this fact that when you raise the primitive root to half of its order, you get -1 from the homework. And it's only really one line long. What a nice proof of Wilson's theorem using something we just learned pretty recently. So, okay, I'm gonna call it good. I had a couple other problems. They have to do with quadratic residues, some of the more recent stuff. I might just bring those on Monday, go over them a little bit with you there.
Is it posted anyway?
I could tack it on. I could tack on a few more problems. Yeah, I went over all that stuff. Yeah, I could. There's not much. I went over most of what I wanted to cover. I just took that one problem kind of got me all screwed up, so that's why I took a little extra time. Sorry about that. Did you have a question?
Can we go over a homework problem?
Why don't I let people go? I'll go down to my office hours and we'll hang out down there and I can do that. But I've already run past time.
Sorry, for the cryptology part of the exam, you know going to give us like 1340 to the 17 power congruent something?
That's why you're bringing a calculator. So the calculator gives me a little more flexibility on what I ask you to do. But I mean, I won't make the numbers too ridiculous. But I don't want to make a problem where you can just kind of guess.
Is it a non-calculator test?
You want a non-calculator test? Nah. Bring a calculator. Yeah, Nicole?
Are you going to be giving us the table for the letters?
Oh yeah. The how you
table,
convert.
the
Yeah.
conversion one?
So for cryptography.
Yeah.
Yeah. If I have some conversions, I probably will try to avoid needing to use that. I haven't written the test yet, but if I need the conversions from letters to numbers, I'll give that to you. Please don't sit home memorizing. Oh, A is 0, 0, B is 0, 1, all that stuff. Don't worry about that part. Okay. So I'm going to go downstairs right now. If there are people that have questions on the homework or want to talk a little bit, I can do that. Otherwise, we'll call it a day. What do you think, Bora?
I like it.